Well, the last thing I left you all with last time, there was a theorem that we did, a longer one was like the direct product and stuff. That's proved in your notes and it's just kind of tedious, so I'll let you look over that at your leisure. I want to look at this one right here. Suppose we have, subgroups, H and K, G, and they satisfy two conditions. Number one, they're both normal, right? So they're both normal subgroups. And number two, their overlap is as small as possible. Their intersection is the identity. Then K is isomorphic to the direct product of H and K. Okay, let's see why this works. First of all, let me point out, HK is always a subset of G, right? And here we know it's a subgroup because of this condition here, right? In fact, all we need is one of these to be normal. In fact, you don't even quite need that. But as long as even one of these is normal, then this is actually a subgroup. So, H and K is R normal, then HK and G is a subgroup. And I think it's probably best that we start off saying that we sort of know what we're talking about. Let me also make another observation. We've actually done this via actually homework problem. I want to make sure that's clear. Pick two random elements, one of them in H and one of K, and consider consider this element right here. By the way, this is a commutator, right? I'll remember that. I claim that this is in H. You might tell me why? Yes.
So we know that H is normal in G, so any conjugation of H is going to be within H. So that's an H.
Good.
And then multiplying it by an element of H, we're going to state H.
Right. What he said. This is a conjugate of H by something in G. So since H is normal in G, this is an H, and this is an H, so the whole shebang's an H, right? Now you see I can pull the same shenanigans in a different order, if you will. This is also in K for essentially the same reason. This is a conjugate of something in K, right? And K is normal, so this thing is in K, as is this. So this thing lives in H intersect K, right? Are you okay with this? But what is H intersect K? It is the identity. So H inverse K inverse HK is equal to 1. So this commutator is 1. So that means that the elements H and K commute with each other. You can just multiply this out if you like. K inverse HK is H, and then HK is K. This is an important and useful observation that we will use in C. I'll send an email about the office hours on Friday as well. Okay, so now define F. I know that's a subgroup. And here's what I'm going to do. Okay, my input looks something like this, right? my output needs to be an H cross K, so it needs to be an ordered pair, right? First entry in H, second entry in K. Agreed? What's the easiest thing that I can do given my parameters here? Do you think? Yeah, well, I'm dying to do that, aren't you? Just do it that way, right? This is the way I'm going to define my function, but there's something I should check first. Like, what's a possible concern? Very good. It's well defined. Right? I could have a problem if I could write HK as a different way. If I could write it as H1K1, right? Then I've got a problem. I agree with that. And in fact, as it turns out, I can. So let's check this.
No.
Let's suppose that I take the element HK in HK and suppose that I can write it another way as H1K1. Let me manipulate this a little bit. I'm going to multiply first on the whichever side this is, the left side by H1 inverse. H1 inverse K is equal to my bad. H1 inverse HK is equal to K1. That's multiplying on the left by H1 inverse, so it kills that one. Now I'm going to multiply on the right by K inverse. Look at this little equation here. Notice this is two different ways to write this same element. Everybody agree? I could write it this way, I could write it this way, right? Notice that the left side of this is in H, right? Same element, the right side is in K. And once again, the fact that this intersects trivially comes up to help me out. So what does this mean? This means that H1 inverse H is the identity, right? And this implies that H equals H1 and K1 inverse is, I'm sorry, K1K inverse. K1K inverse is also the identity, which implies K equals K1. So in other words, HK, which is H1 K1 so this function is well defined. In fact, more than just well defined, there's something else we should take away from this. And the other thing that we should take away with this is look what we've proved. If I can write this way and this way, then the H's match and the K's match. So in other words, in HK, there's only one way to write this. That's essentially what that proved. Everybody okay with that? Now, I need to show a couple things. I need to show that this is a homomorphism and that it's one-to-one and on. but this part will be easier, I think. Let's do homomorphism first. Suppose that F of HK times H1K1 I need to show that this is a homomorphism. Now I'm going to use notice, remember how the K's and the H commute with each other, right? So I can rewrite this as F of H1 K1. Right, because that H1 and that K and that H1 I could swap, right? Because they're in different pieces. And what is this? This is H1 comma K1, because I know this is well defined. And by our rule of multiplying in the direct product, this is HK H1 K1. And this is F of HK, F of H1K. Okay, so it's a homomorphism. Everybody okay with that? Got to show it's one-to-one and onto. I think onto is fairly easy. Actually, that's one-to-one is too. Suppose I have an arbitrary ordered pair in here. Then HK is F of HK. Check. Everything's covered, so it's onto. How about one-to-one? Suppose that HK is in the kernel of F. Well, this implies F, whoops. Not the ordered pair, HK should be in HK. This means that F of HK is the identity of the direct product, which is the identity of H, identity of K, which is HK. Therefore, H equals the identity of H, K equals the identity of K. So HK is the identity of, well, G as a matter of fact. Actually, these are all identities of G. What I wrote there is true, but let me think of it more inclusively as the identity of this. Therefore, kernel of F is the identity of G, which is the identity of HK. So F is one-to-one. So this is actually a nice criteria here. Let me give you a corollary, because this corollary is going to help us determine exactly when something is a direct product of its subgroups, or some of its subgroups. Any questions? Yes.
So proving one-to-one, why did we assume that it was in the kernel?
Because all you have to do is show the kernel is trivial. And so that's my little correction, right? I mean, one-to-one if and only if the kernel is the identity. And remember, that trick for showing that a function is one-to-one only worked for homomorphisms. If this was just a map of sets, you have to do it the old-fashioned way, where you assume f of x equals f of y, prove x equals y. Yes?
When was that covered?
Back when we first talked about homomorphisms. Yeah.
After
I don't remember. Ask me after class, I'll look it up for you. Corollary, actually, you also saw this in linear algebra, as a matter of fact. So that's one thing that I can point back to as well. Do you remember a linear transformation is one-to-one if and only if the null space is zero, Right, that's exactly the same theorem. Right. Let's see. Definition. Oh, no, I'm not. Let H and K be subgroups. This is 718. Such that number one, H and K are both normal in G. Number two, H intersect K is the identity of G. Number three, HK is all of G. And this almost requires no proof. Because these first two steps were from the previous theorem, and the conclusion there is HK is isomorphic to H cross K. But if HK is equal to G, then G is isomorphic to H cross K. So this is just really an observation, but it's an important thing because this allows us to tell when a group can be decomposed as a direct product subgroup. If you have two normal subgroups, such that when you put those two normal subgroups together, you get all of G, and their intersection is trivial, and they're both normal, then G is isomorphic to the direct product of those two subgroups. And we saw this the other day. We broke up, for example, Z6 into a copy of Z2 and a copy of Z3. Let me give you this definition that you've already seen in your homework. And we're gonna take a moment to kind of look at some of the more general properties of semidirect products. Definition. Let's suppose that H and K are groups. And P, a homomorphism that goes from the group K to the automorphism group H. Then we can put a kind of a fun group structure on this as follows. We define the semidirect product strange notation here, to be the set of ordered pairs so the underlying set of the semidirect product is exactly the same as the direct product. It's just all possible ordered pairs, first coordinate H, second coordinate K. But the way that I'm going to multiply them has a little twist to it. And actually, twist is a descriptive word because I'm going to say H, K, H1, K1. The way I'm going to multiply this is in the second coordinate, I'm going to do just what I do in the direct product, straight up K times K1. Okay, so it looks like the direct product so far. The first coordinate, I put a little twist on it. if I did that, it would be the direct product, H times H1. But I'm not satisfied with this. I want to have a little bit more fun and joy in my life. So I'm going to put a little twist on it. Now remember, this phi of k in the middle is an automorphism. And, well, phi is an automorphism, and it takes k and it spits out an automorphism of h. So this thing right here, phi of k, is an automorphism of h. So I've got something in h times this automorphic image of h1, which is also in h. So this is indeed something in h, right? Now, whether this makes sense, yes.
You said phi is an automorphism. Is that true?
No, it's a homomorphism. But, yeah, I'm sorry, but this is the way it is. Phi is a homomorphism from here to here.
Okay, yeah.
But the output is an automorphism.
Yeah.
Now, you actually showed in your homework that this is in fact a group. I just argued for closure because certainly the second coordinate is in K, which is where you need it. And the first coordinate is something in H. And then this thing right here is an automorphism of something in H. So this is again in H. So at least this is barfing out something that has got a first coordinate in H and second coordinate in K. What is not clear is this is, for example, associative. What is the identity? What is the inverse? And you did that in the homework. This actually gives an example, or this actually forms a group. Now, one of the things that always bothered me when I first saw this definition, I guess is sort of a natural question that might leap to your mind is, okay, this seems very contrived. How do you even know that there is a homomorphism from K into odd H? But I'm here to tell you, there is always one homomorphism at least. Can anybody give me an example? Now it's time for you to be a smart aleck. Can anybody give me an example of a homomorphism from K into odd H? It's always there.
Said anything in K.
That is correct. One example. Phi from K into odd H. Let me tell you how it works. Phi of K is the identity of odd H, which is, this is the identity function to take each H and H to itself. Okay. If I take this particular automorphism, or I'm sorry, homomorphism that dumps everything in K to the identity, what does this rule do now? Yes,
It's just a direct product.
that is correct. So in this case, in this special case, we recover the direct product, which is good. In mathematics, you should always kind of have full circle like this, because what happens here is phi of K, this just turns into the identity automorphism. And so my first coordinate is just the ordinary H times H1. So you recover the direct product. But if this has got a little bit more sparkle to it, a little bit more pizzazz, then this can be more exotic. And actually, another thing we saw in that homework is the dihedral group on the n-gon for n bigger than or equal to 3 is always a semidirect product in this fashion. Okay, any questions? Right. So let me give you the following theorem here. I'm going to give you this. I'm going to give you a theorem that's analogous to this one, only it's for semiconductors. Theorem 7.13. let's let, G be a group and H and K subgroups. Subgroups. Such that. Number one. H is normal in G. Number two. H intersect K is the identity. And number three. HK is all of G. Then G is isomorphic to HK. Up down there. For some phi from K into odd H. Okay. This is just like that theorem that I gave you about the direct product. Only it determines when something's a semi-direct product. Anybody notice what the difference is on the conditions between the direct and the semi-direct here?
The H needs to be converted.
That's right. For the direct product, I needed both those subgroups to be normal. For the semi-direct product, I only need one of them to be normal, right? So notice also, it turns out that if K is also normal in H, then the semi-direct product you get is the direct product, right? But if only one of them is, you get something more interesting. So let's see why this is true. Proof. Since G is equal to HK, it suffices to show that HK is isomorphic to H semi-direct product. Now, what we need to do, yes,
Think back to what you just said. So you said if K is normal in G2, then it's the direct product. Is that like necessarily true? That if K is also normal in G, then it has to be isomorphic to the direct product? Does that make any sense?
yes, if K is also normal, then it'll be the direct product.
It'll necessarily.
Yeah, which is a special K, so it'll be a semi-direct product. It'll be that particular special case.
Okay.
Right. Okay, so really, I think the burden on us is to find what's the fee, right? That's something that I seem to pull out of the thin air. Before I can even talk about an isomorphism there, I guess I better talk about that, right? Well, let's see if we can define it. Anybody know how we might define this? This is actually an old friend, maybe, or maybe an old enemy, frenemy, something like that. How about this? Where? What do I mean by P sub K? This should be an automorphism of H. You remember this automorphism, this subscripted automorphism, where phi of h is the conjugate, where k is fixed. That is going to be that is going to be our homomorphism. Input k, output phi sub k. This is an automorphism. Now, why does this work? And this, I think, if you look at the proof here, this sheds light on why we did this because the definition of the semidirect product, I mean, it almost seems like some kind of crap that Gandalf came up with after hanging with Bilbo for a while or some business like this. Where did this really come from? I think that this kind of shows. Define F from HK into semidirect product. And we're going to define it this way. F of HK is equal to the order pair HK. This is just the freaking thing we did for direct product, right? This is also well defined as before. The key thing here being the fact that the intersection of these two is one. Remember how we did the well-defined before, and we found that if you wrote something in terms of HK, then that was unique. It's exactly the same proof, right? So this is a well-defined homomorphism again, right? Well, I ran my mouth too much. Well-defined for sure, it's a function. Homomorphism, I'm not so sure yet, right? We need to verify this. So well, let's see what happens here. Let's look at F of HK times H1K1. Now, I need to be able to rewrite this as I would desire, right? This function was only defined when I have an H and then times a K. And look what I've got here. I've got an HK and then an H and a K. Oh dear, what will I do? There's one piece of leverage that I haven't used yet. And that is the normality of H, right? But let me write this more grammatically. Now, I'm going to insert something in that slot in here. Any guesses what I might do? And remember, I'm trying to leverage the fact that H is normal. Yeah.
A inverse K.
Good. I'd like to do that. I really would, because now I've got a conjugate of H1. So this blob will all be an H. Everybody agree with that? But now I've inserted that, so I've got to cancel it in a certain sense. And that's why I get the other two. These two vanish. Everybody okay with that? So this is, for emphasis, F of H and then K H1 K inverse times K K1. Right? This blob is in H because that's in H and H is normal, so that's in H. And this is in K, right? So I can use my function to write it this way. So this is, what the heck is it? This is H K in HK H1 K inverse. I'll write it kind of like that. and then K, K1. I agree with that. But okay with that. But can anybody further identify what that thing is? Yeah.
B sub K of H1.
Right, because remember what the automorphism does, is K H1 K inverse, that's exactly this. So I can rewrite it again this way. H B K of H1 K K1. And this is exactly the rule for the multiplication in the semidirect product. So even though that definition probably looked contrived, this is exactly where it comes from. This is the genesis of it and why it had to be the way it was. That's exactly what's going on. So in particular, this is F of HK, F of H1, K1. So F is a homomorphism. One-to-one and onto are as improved of direct product. In other words, there's the machinations you go to prove it's one-to-one and onto are exactly the same as what we did in the previous. Yes.
Can we go back to just the definition of F? How do we know, and maybe this does make sense, how do we know that we can go from HK to H comma K when we have this pure semi-direct product? Like, how do we know that,
How we know we can go from?
are we just defining it like we can, because how do we know that HK
Well,
lives in
because
H?
in HK,
Yeah,
like HK is my domain. Everything in HK can be written in this form. So I take that. And now I'm just saying, this is how we define it, right? And of course, the first question on your mind might be, well, is this well defined? Can you do this? Well, we actually proved that for the direct product, and the proof is no different, because what we needed for the direct product was only this condition here.
okay, right, yeah.
Okay, good question. Others? Yes.
For theorem 7.1.13, it says that G just equals the semidirect product. So it's, does it really make a difference if it's that or?
So, okay, so yeah, you're picking apart something that's, I probably should talk. Yes, in the note, HK equals G, and so let me show you the difference. It's a subtle difference that doesn't amount to much, but so let me give you an example here. And let me do this with direct products, because your question is essentially the same for direct products. It's all, so do you remember this from last time? This is called an external direct product. Z6, if I write this way, and this is 0 bar, 1 bar, well, let's see, 0 hat, 1 hat. And if I write this as 0 star, 1 star, 2 star, I put the little different hats and such on these to differentiate that all this addition up here is taking place mod 6, right? Because 1 plus 1 is 2 here. This is taking place mod 2. Here, 1 plus 1 is 0, right? And that's why I put a hat and a star. It's different, right? Z6, this is sometimes called the external direct product, because here's what happened. I took this guy, and I jammed them together in a direct product, and I said, ooh, it's isomorphic to this. That's an external one. I can also consider this to be an equality if I consider an internal direct product, But see, here's the difference. Neither one of these are subgroups of this. If I wanted to make it an equality with an internal direct product, this is actually 0 bar, 3 bar, direct product, 0 bar, 2 bar, and 4 bar. Right? And now, instead of writing 0 hat, 1 hat, I've got the real 0, 3. Notice 3 is of order 2, just like this is, right? But see, these are now proper subgroups of this and so now what I've done is I call this an internal direct product, because what I've done is I've plucked the subgroups out of the group and said, oh, look, it's a direct product. The distinction is not really worth having your hair fall out over this one, so. Okay, good question though. Others? Okay. What we're going to do is we're going to start on as I promised, we're going to talk about finite abelian groups. In general, hard to classify, hard to list all of them. But one of the kind of crown jewels that we're going to have is we're going to be able to, if I give you a finite abelian group, if I give you a number, 125 or 274 or whatever, you will be able to tell me exactly how many different groups there are of that number, if they're abelian, right? Non-abelian, that's a bigger amount to fly. So we're going to look at the structure of, in fact, more generally, in some cases, finitely generated abelian groups, but finite abelian groups, we're going to be able to list them all. And in fact, there'll be kind of a canonical way. I'm going to show you a couple of canonical ways that you can figure out the structure of these groups. So this is there's kind of a nice end game to this, because we're going to understand what all finite abelian groups look like. This is incredibly important all over the place in mathematics. Coding theory, factorization theory, anything where you need to understand where there's kind of a group structure, lots of counting problems. And in fact, I can give you some very simply put, even though we're going to understand the structure of finite abelian groups, I could give you some interesting, very simply put, open questions that will get you fortune and glory if you could solve them, even though they sound simple. They quite difficult to tackle. Let me start off with this limit here. And this limit is actually really kind of groovy if you think about it. Suppose you have an abelian group of order Pn. Let G be a finite abelian group of order P to the n. And here by P, I mean a prime. P bigger than 0 is a prime. Then by the way, what do we know about this? Well, it's a P group, isn't it? And we actually know from the homework that I was going to say it has normal subgroups. Well, no surprise there, right? Because this group is abelian, any subgroup is going to be normal. But here's what we know. We know there's a subgroup of this for P to the K for every K between 0 and n, right? There's a subgroup for Pn minus 1, Pn minus 2, all the way cascading down, right? We know that. And of course, Cauchy's theorem from back in the day tells us that there's a subgroup for P, right? Here's kind of a groovy result about this. G is cyclic. If and only if G has 1 and only 1 subgroup. of order P. Cauchy's theorem tells me that G, if it's of order P to the n, it has to have an element of order P. And of course, that element of order P generates a little subgroup of order P in there. If G is cyclic, then there's only one of these subgroups. We already know that, right? Because one of the things that we know earlier from our classification of cyclic groups is if you're cyclic, then there's one and only one subgroup for every divisor of the order of that group. So if it's cyclic, then there has to be only one of them, right? The other direction is interesting because if that's all you need to know. If there is only one subgroup of order P, it has to be a cyclic group. This is kind of intriguing because there's lots of subgroups of this, but you can key on the ones of P and say to yourself, hey, self, does this group have only one subgroup of order P? If the answer is yes, cyclic. The answer is no, not cyclic. So let's prove this. So let's start to prove this. If G cyclic, then we know there exists a unique subgroup of order K for every K dividing the order of G. Okay, so in particular, there exists a unique subgroup of order P. Okay, well, there's one dragonfly right there. If it's cyclic, there can only be one subgroup of order P. And of course, we know the subgroup of P exists from our homework, Cauchy, a number of sources, if you will. How about the other direction? That's the intriguing one. How about strategy? Any ideas on how we might, so what we're trying to do is if G is a finite abelian group of order P to the n, we're trying to do is we're trying to show that if G has one and only one subgroup of order P, then G is cyclic. Any ideas on a strategy, an effective strategy? Yes.
Well, it kind of looks like CeeLo because we have order P to the n. And then when I hear one subgroup of order P, I'm thinking normality, the CeeLo theorems.
Right, but here's the thing. The group's abelian, so everything's everything's normal. Let's go by induction on this, right? Where order of G. Well, okay. If we go by induction, the first natural thing, I guess, I don't want to start at 0 because that's the identity group. I'll start with n equals 1. Well, if the order of G is P, then G is cyclic. We already know that. So we've got the conclusion there. So the one case is done. Assume we assume statement holds. For all abelian groups of order e to the k for k like 1 and say some m. Right? So we've got that it holds for e to the first power. Now we assume that it holds for all the way up to 1 to m. We have to show statement holds if the order of g is in fact p to the m plus 1. We will finish this later, but here's what the strategy is going to be. That group G will have a element of order P in it. We mod out by that subgroup of order P, taking us back to the inductive hypothesis. That's essentially what's going to happen, and we'll see this play out next time. Any questions? All right, I will see you folks on Friday. Thank you.